So we kind of realized that area and functions are related in that when you integrate, you find the area under the curve, but you also find like the amount of change from the original function. So today we're going to be looking at actual geometric areas to help us find integrals. So once you've learned this, I can give you, and I will give you, a bunch of graphs that just have like curves on them or features on them that you'll have to break apart to find the areas because you won't be given a function. This first one, the integral from 1 to 3 of 4 dx graphs me a horizontal line here. And if I'm going from 1 to 3, 1 is right here, 3 is right here. So I'm finding the area under the curve between these two lines. What have I formed? A rectangle. So this is a rectangle with a height of 4 and a width of 2. So therefore the area under the curve is base times height. 2 times 4 is 8. There's no need to do like calculus math there, even though we're in calculus, and that is calculus. The second one, the integral from 0 to 3 of x plus 2 dx graphs me this line. And if I'm going from 0 to 3, then here's 0 and here's 3. So if I draw lines up, what kind of shape have I made? A trapezoid. So the area of a trapezoid is found by using the area equals 1/2 the height times base 1 plus base 2. Here it is right here. Good, I remembered it correctly. Oh, this is not the trapezoid rule. We're just making a trapezoid. Luckily, if you forget the trapezoid rule, you can also, and I recommend doing this because I'm going to give you some sort of graph that has trapezoids on it, you can forget the trapezoid rule, but still break this apart into a rectangle and a triangle. And if you do that, then you can sit here and calculate the area of this rectangle, calculate the area of this triangle, and then you have your total area, okay? And if you really look at the area of a trapezoid, you can see the area of a rectangle and the area of a triangle embedded within that. Anyway, in this case, the height, so we have a height of 3. The height is the distance from one parallel side to the other. Even though this is not really the height, this would be maybe people consider the base. The height is from one base to the next. So that's 3. And then we have base 1 and base 2. That's the length of this and the length of this. So we have 2, and then 1, 2, 3, 4, 5 for a total of 7. 1/2 times the height, so we have 3/2 times 7, which becomes 21/2. That's using the area formula for a trapezoid. Otherwise, you have 2 times 3, which is 6, and then 1/2 times 3 times 3, which is 9/2. 6 plus 9/2. You'd wind up getting the 21/2 as well. Okay? That's your second major shape that we're going to see. The third major shape that we're going to see is a semicircle. Your general formula, or general equation for a semicircle, general equation for a circle would be pi r squared, unless we're working in coordinate geometry, and then we're going to see something that looks like this. If you want the full area for the circle, you'd multiply this times 2, but we only have a semicircle here. So the square root of 4 minus x squared in this case, because of the fact that the radius here is 2, we wind up with a 4 there. So these things are all related. It's like x squared plus y squared equals r squared, r being the radius. You should have learned that, right? You learned that? Somebody nod your head yes to make me feel better. Okay, thank you. Okay, so the integral from -2 to +2, because our semicircle starts at -2 and goes to +2. So this is like just the formal notation, the formula that generated the semicircle dx. Well, it's a semicircle, which means it has a radius here of 2. And we know that the area formula for a circle in general is pi r squared. So therefore, 1/2 pi r squared gives us the area from our semicircle. We know that the radius is 2, so therefore we have 1/2 pi times 2 squared. Simplify it down and you wind up with 2 pi in this particular case. Okay? These are all just general examples of how you can use areas. So you have a rectangle that's formed, you have a trapezoid, or even really a triangle that's formed, and also a semicircle that's formed. Okay? If I just gave you a quarter circle, then instead of 1/2 here, we'd use 1/4. We have a couple special definite integrals as well. If my bounds are exactly the same, if I integrate from a to a, then what that means basically is I start here and I end here. Do I have any area formed? No, I don't have any area formed, so that's why we get an answer of 0 with something like that. So if you see same bounds, then the answer is going to be 0. Another one is if I reverse, or for some reason I want to reverse my bounds. So instead of going from a to b, I go from b to a for my function. If I want to reverse those, I can do that by simply putting a negative sign out front, and that reverses the bounds for the same function. So for example, sketch and find the area of the region that corresponds to the integral from 0 to 4 of 2x dx. So it says sketch and find. So I give you the graph already, and then we want from 0 to 4. So here's 0 right here, here's 4 right here. So I'm going to draw a line up, and that gives me this area right here, which is a triangle, of course. So we're going to use the triangle area formula rather than try to evaluate this using our sums. Okay? So I'm just going to write the area equals which is 4, length of 4 right here times the height, which is 8. Okay, so we get A equals 16. Much simpler, and that would be square units. If I gave you like centimeters or something like that, then you'd write centimeters squared. But much simpler than trying to find the area using your summation from I equals 1 to whatever and a bunch of rectangles and all kinds of stuff. It would take forever. Much easier here. How about this one? The integral from pi to pi of sine x dx. What do we get? 0, because we went from 1 to the same thing. So we get 0 here. And on this one, what do you notice that's weird there? Yeah, the numbers are reversed on my bounds. I should see a 3 here and a 0 here. I should go from low to high. Okay, it should be smallest number, biggest number. So in order to fix that issue, throw in a negative sign out front, and I get negative out front integral from 0 to 3 of the exact same function. Problem solved. As usual, all year long, we've been saying you can split stuff up. We can split stuff up here as well in a slightly different way than normal. So let me draw a little number line here. And I'm going to say here's A and here's B. So this is like, pretend that's the x-axis. If I throw another number in here and call it C, it could be anywhere in between A and B, then I can split my original integral from A to B up into the integral from A to C plus the integral from C to B. And that's exactly what I'm showing here. The integral from A to B of my function dx equals the integral from A to C of my function dx plus the integral from C to B of my function dx. That is really helpful to use when you're working with a function that is continuous, like I have written there, I guess, but it's going to be easier to work with if you break it into a couple of different pieces like an absolute value function. So with this example right here, and I thought I had a graph on here, but I guess I don't. So the absolute value of x is graphed by making a v. If I'm taking the integral from 0 or from -2 to +2, let's say that's -2 and that's +2, then it's going to be easier for me to integrate from here to here and use a triangle area, and then also integrate from here to here and use another triangle area, and then add those two things together. That's what this property right here allows me to do. My last two properties here, the integral from a to b of a constant times a function dx, I can pull that constant out. So it's like if I want to factor out a GCF or something like that before I integrate, I can do that. The second one, the integral from a to b of two functions being added together. That's our usual thing that we talk about. If I have an integral of a function that has several terms, that would be this case right here. I can apply the integral to each term individually. So I can split the functions up. That's okay. So let the following rules be true. Basically, we're applying these little properties that we just learned about. I'm telling you that the integral from 1 to 3 of x squared dx is 26 thirds. I'm telling you that the integral from 1 to 3 of x dx is 4. And I'm telling you that the integral from 1 to 3 of dx is 2. So what do I really have here? Not just dx. 1, yeah. The integral from 1 to 3 of 1 dx is 2. Okay? Geometrically, if you wanted to sketch that one out, this would be 1, right? So here's my 1 from 1 to 3. I'm just making a rectangle with a height of 1 and a length of 2, so I get 2. Okay? So I'm just telling you that these three integrals right here are true. On the homework, there's going to be a set of problems that are like that. They're just telling you the integral from blah, blah, blah is this number. So then we want to evaluate from 1 to 3 the integral of negative x squared plus 4x minus 3 dx. To do that, you want to split this thing up and turn each integral that you're looking at into something that you're given, and then you can substitute in that value. So the first thing I'm going to do is split this into each separate term. The integral from 1 to 3 of negative x squared plus the integral from 1 to 3 of 4x minus the integral from 1 to 3 of 3. And then there's a dx on each one of these, just to complete the notation. The first term, we're going to pull this negative out. That's right. So now we have the negative integral from 1 to 3 of x squared dx, which matches this. Then, pull the 4 out. Integral from 1 to 3, I pulled the 4 out, and I'm left with the x dx, which matches this. Then minus, factor out a 3 from 3, and you get the 3. Integral from 1 to 3 of 1 dx, or just dx. So now I've made each one of these integrals match something that I was given. And now I can substitute in. The integral from 1 to 3 of x squared dx is 26 thirds, so I get negative 26 over 3. Then plus 4 times the integral from 1 to 3 of x dx is 4. Minus 3 times the integral from 1 to 3 of 1 dx is 2. So, add them all together and you get your answer. This is 16 minus 6. And then I got this negative 26 thirds. So negative 26 thirds plus 10. So that's 30 thirds. So I have 30 thirds minus 26 thirds. So it's 4 thirds.
Buddy, if you're not going to speak up, we're not going to listen.
Yeah. The directions say evaluate the definite integral by the limit definition. So I'm not telling you what the integral from 1 to 4 of x squared is here, so you have nothing to substitute in, which means that we have to use the limit definition, which means we're back in where we have been for the last couple of days. Okay? What I can do, though, is make my life a little bit easier by doing something here. I'm not going to sketch it either. What can I do to make my life a little bit easier? Yeah, the 4 can come out. So I get 4 integral from 1 to 4 of just x squared dx. So whatever I get here, I'll multiply that by 4, and then I'll have my answer. Okay? Now, we want to use the limit definition, so what do we need to do? I'm not going to sketch it. I need to switch from this pretty notation to the sum notation. So this becomes the limit as n approaches infinity of 4 times the sum from I equals 1 to n of, no, f at c sub I times delta x. Okay, delta x is 4 minus 1 over n, so I get 3 over n. You have your choice. You can use left endpoints or right endpoints here. Right endpoints. So c sub I equals 1a plus I times delta x, so we get 3I over n. So, okay, you can do f at c sub I equals. So is the function 4x squared, or is the function x squared? The function is now x squared because I pulled the 4 out. So all I need is 1 plus 3I over n squared, which is terrible. 1. Perfect. 6I over n. 9I squared over n squared, almost. Squaring everything. 3, the I, and the n. Right. This is this. And delta x is this. So now we have the limit as n approaches infinity, 4 sum I equals 1 to n. We haven't done any converting yet, of 1 plus 6I over n plus 9I squared over n squared times 3 over n. Okay, now it's all written down nicely so that everybody sees that we know what we're doing. Now what do we do? Pull out the 3 over n. So now I have the limit as n approaches infinity. The 3 over n, where can I write that? How about 3 over n here times 4? So actually I have 12 over n. We're going to split it. Sum I equals 1 to n of 1 plus 6 over n sum I equals 1 to n of I plus 9 over n squared of I squared. Okay? Looking good. Now what? Convert, limit, n goes to infinity. I have this 12 over n still, times. This becomes n plus good. Now what? Okay, we're going to divide out some stuff. No, there's no easy way. Everything is good. Yeah, we got an n here and an n here and here and here, so we can do that. Gone. This is 1. Gone. Gone. Anything else? The what? The 6 and the 2 can reduce. This is now 1, and this is 3. This is, what is that? That's a 9 and a 6, so that can reduce 2 and 3. Anything else? They shut you down. Okay, that's plenty of canceling. Let's rewrite it. Let's go raspberry. Limit as n approaches infinity of, I still have that 12, parentheses, 1, okay, 3 over n squared times, yeah, let's FOIL that. Okay. Thanks. Anything else to get rid of? I don't think so, until we start distributing more. So let's keep going. Limit n goes to infinity. The 12 times the 1 plus, so 3n over n, which is just 3, then plus 3 over n, six n squared over 2n squared. The n squareds are gone. 6 over 2 is, so plus 3. Then 9n over 2n squared. 9 over 2n. Then 3 over 2n squared. Throw the 12 in there? How about I don't? Because right now I can take the limit as n goes to infinity, right now, before I even combine like terms, and all the n terms in the denominator are going to disappear, which leaves me with the 12 times 1 plus 3 plus 3. So I get 4, 7 times 12, which is 84. Okay? So the area under the curve from 1 to 4, 4x squared dx, is 84 square units. That does it for the section, I think. Yeah, that's it.